Hi, this is Raphael Mudge, the creator of Cobalt Strike. Welcome to Part 2 of Red Team Operations with Cobalt Strike, Infrastructure. In this lecture, I will introduce you to listener management within Cobalt Strike. And I will introduce you to the different types of beacon payloads and how to configure them. In Cobalt Strike, a listener is a configuration for a Cobalt Strike payload. And where applicable, a listener is also the configuration for the payload controller or server. There are three types of listeners in Cobalt Strike. An egress payload is a payload that beacons out of a network. A peer-to-peer payload is a payload that communicates through a parent payload and is primarily used for pivoting. An alias is a reference to a payload handler elsewhere. To manage listeners, go to the Cobalt Strike menu and click Listeners. This is the listener management interface in the Cobalt Strike product. Here you will see a table with a summary of the different configured listeners. Press Add to add a new listener. And when you see the new listener dialog, make sure you give your listener a name. Every listener gets a name. And choose the type of payload that you're configuring. I want to foot stomp the name piece for just a moment. The name is very important because it is what your teammates will see when they are using the tool. And it is very important that the name is descriptive enough that your teammates know the purpose of the listener and have an idea of its characteristics and potentially performance limitations as well. When you select a payload type, the new listener dialog will change to have payload-specific options that you can configure. This slide summarizes the types of payloads in Cobalt Strike that you can create listeners for. One topic I do want to cover right away is the topic of payload staging. Periodically throughout this course, you will hear me refer to stagers and stageless payloads. A stager is a tiny program that downloads a payload and passes execution to it. Stagers are necessary in some attacks because the attack might have very limited space for payload content. A great example is using a PowerShell one-liner for lateral movement. I can't fit a 200 kilobyte beacon payload in a single PowerShell one-liner. So that situation requires a stager. If you hear me refer to stageless, that means the attack or automation uses a payload as is, and there is no stager involved in that process. In Cobalt Strike 3, stagers were used in all of Cobalt Strike's automation. They were a default. In Cobalt Strike 4, stagers are no longer as prevalent in Cobalt Strike's workflows as they once were. Most post-exploitation actions in Cobalt Strike 4 are stageless. But some of the legacy user-driven attacks in Cobalt Strike still use stagers. And you'll hear me use this terminology to explain when one behavior is happening or another. So I wanted to make sure that you were aware of it. And you may ask, what's the big deal? Why do I, as a red operator, care whether an action uses a stager or it's stageless? Well, stagers are, again, these very tiny programs designed to fit in size-constrained attacks. So in Cobalt Strike, the stagers do not authenticate their payload controller. So they are less secure than just using a stageless payload. They are also more brittle. While there is some resilience to different error conditions built into the stagers in different places, it's not full coverage of everything that can go wrong. So you do run the risk that your stager could crash if something it didn't expect happens. The stagers in Cobalt Strike, again, because they are based on the stagers from the Metasploit framework, they are easier to detect. The content of the stagers is well understood, and any kind of memory scanner should be able to pick these out of memory right away. And there's no capability in the Cobalt Strike product to clean these up out of memory or to obfuscate them. So it's very much to your advantage to do without them where you can. I want to share a little bit more detail on payload staging, because even though it's something I de-emphasize in Cobalt Strike 4, the fact it exists and is possible enables some features in Cobalt Strike, and it has some implications we're going to talk about a little later when we discuss team server operational security. So it's going to really help to actually understand what is happening when you're staging, because everything else will become clearer a little bit later on. So we have our controller, right? Our payload controller. And that controller could be, in this case, Cobalt Strike or the Metasploit framework. It doesn't matter because Cobalt Strike is compatible with the Metasploit framework's staging protocol, at least for HTTP and HTTPS. Now, here is what happens when we send a document, like let's say we send a macro-enabled Word document over to a target, and it spawns a child process, and it injects a payload stager into that child process. That payload stager starts to run. And the staging protocol for an HTTP or HTTPS stager is to make a GET request from its controller. And the GET request is just a GET, and it is a URI that checksums to a certain value. I forget what that value is, but anything that makes a request that matches this checksum is given as a response a position-independent blob that runs your payload and sets it up in the stager's process space. This is the Metasploit framework staging protocol. And if you make that kind of a GET request on a Metasploit framework handler, you will get back a Meterpreter payload. If you make this kind of request on a Cobalt Strike web server, by default, you will get back a Cobalt Strike beacon payload. Something that is really cool, though, about this compatibility, there are some benefits. First, let's say the Metasploit framework happens to have a very interesting user-driven or client-side attack that you want to use to deliver the Cobalt Strike beacon. You can set up that attack and specify your Cobalt Strike server as the L host and L port of your Windows Meterpreter reverse HTTP or reverse HTTPS payload. And the Metasploit attack will make this same GET request and download and run a Cobalt Strike beacon instead. So that allows you to use a Metasploit framework exploit to deliver Cobalt Strike's beacon seamlessly. The other kind of cool benefit in Cobalt Strike is that I can configure a stager that points to a running Metasploit framework instance and inject it instead of a Cobalt Strike beacon payload. And in this way, I can pass a session from Cobalt Strike to a Metasploit framework instance, or I can pass a session from a Cobalt Strike instance to another one that I'm not connected to, but I'm just aware of. And this method of session passing, by configuring the parameters of a payload handler elsewhere, is the concept of foreign listeners in the Cobalt Strike product. And I will demo those later in this course as well. But the three big takeaways I want you to understand is staging is what allows us to use a Metasploit framework exploit to deliver a Cobalt Strike beacon payload. It is also what allows us to pass sessions to the Metasploit framework. But because there is a predictable way to download a Cobalt Strike payload, it also creates a big OPSEC concern as well. And so we're going to talk about that later in the next lecture when we talk about Team Server OPSEC. So that's what I want you to know about staging right now. I know that's a lot of background material with the promised payoff later on, but if you're with me so far, I will definitely get to each of these topics in the right spots in this course as we progress. I just realized I don't have a slide to talk about the behavior of the HTTP beacon and to introduce it. So I'm going to get my money's worth out of this Wacom tablet and draw out an explanation of the HTTP beacon and how it communicates. So here we have our Cobalt Strike controller, and it is running a web server. That could be, say, on port 80. And over here we have our process on our compromised target. And inside of that process, we have our HTTP beacon payload. Now, let me explain what the HTTP beacon payload is doing. It's beaconing. What this payload will do is it will connect to the Cobalt Strike C2, and it will make a GET request to some URI. And in that GET request, it's asking Cobalt Strike, its controller, do you have anything for me to do? And Cobalt Strike may respond and say, no, I don't. In which case, the HTTP beacon payload will go back to sleep for whatever time period is configured in the payload profile. And it will wake up later on, and you won't believe what happens next. Blue teams don't want you to do this, but they can't stop you. It makes an HTTP request. And in that HTTP request, it asks, do you have anything for me to do? And if the server has something for it to do, it will respond with an encrypted blob of data that contains all the tasks for the payload to execute. Okay? Makes sense so far? Now let's say that your tasks generate output, something to send back to Cobalt Strike. The HTTP beacon will follow this up with another request that is actually an HTTP post. And this request will contain an encrypted blob with the output for the tasks that just ran. If there's no output, there's no post request. But this is what the HTTP beacon is doing underneath the hood. And in the next lecture, when we talk about Malleable C2, I'm actually going to explain your options to make this very topsy-turvy, because you can actually do some really cool things like have output chunked and sent over many GET requests instead of one big POST request. Or for those check-in taskings that are requesting whether or not there's something to do, why, you could even go so far as to make that a POST request if you really want to. There is that kind of flexibility in the Cobalt Strike product and with this payload. And that's something that's really, really neat about this tool. But now you have an appreciation for the HTTP beacon and what it looks like when it's communicating with you and why it behaves the way it does. Here's the dialog to configure the HTTP beacon. You can set the host that beacon will call home to. You can set the HTTP stager host. And remember, staging is not the default in Cobalt Strike 4, but there are times when pairing an attack with a payload requires a stager. And so this lets you configure which host is used in that case. And of course, you can configure the actual callback port as well. Press the plus button next to host, and you will get a nice dialog to configure the host that your HTTP beacon should call home to. A couple things to point out. You can use a comma-separated list of hosts, just like you always did in Cobalt Strike 3 and before. That's no problem. Cobalt Strike will do the right thing with it. I just kind of want to speak to a couple things. First, fully qualified domains are okay, certainly, like foo.bar.com. A dotted quad IPv4 address is also okay. And if you want to do IPv6, that is okay too. You just need to use the bracket notation for the address. So that's what it looks like to configure a callback host for the HTTP beacon. At the bottom of this dialog, you have an option to set up a proxy configuration for your beacon payload. By default, beacon will take on the proxy configuration for the current user, the same stuff Internet Explorer would use. But if you want to override that, you can. And here's the dialog to do that. You can specify the proxy host, the port, the type, a username, a password, or you can even direct your HTTP beacon to ignore the proxy settings and use a direct connection. I do want to add that these settings affect beacon's payload only. They do not affect the beacon HTTP or HTTPS stagers. All right, let's take a look at setting up the HTTP beacon listener. Go to Cobalt Strike, Listeners, press Add, and here is our new listener dialog. We're going to give the listener a name. We'll call it Local HTTP. Press the plus button, and we'll use 10.0.0.204 as our callback host. Everything else looks good to me. We've got our default port. We have our HTTP stager host. So let's go ahead and press save. And our listener is now started. Great. Now let's go ahead and test it out. Go to Attacks, Web Drive-By, Scripted Web Delivery. This will let us stand up a file on a web server and pair it with a one-liner that downloads that file and runs our configured payload. So we're going to press ... next to listener, and this will let us choose our beacon payload that we just configured. Press choose, and that's configured, and why not, we'll make this a 64-bit payload. Press launch, and there we go. We now have a PowerShell one-liner that will run our beacon payload so we can try out our listener. So I'm going to put that in the clipboard, press OK, and now here I am on a Windows 10 target. For this demo, I've disabled antivirus, We will get to antivirus when we talk about weaponization. But for now, I just want to demonstrate how to use a one-liner to test out our payload. So click on this little Windows Start button, go to Run, and just paste in the one-liner, press OK. And let's jump back over to our Cobalt Strike system. Here we are, and you can see that we now have a callback. It is running in PowerShell.exe, process ID 5340, and this is a 64-bit beacon payload. And you can see it's calling back to the local HTTP listener as the user Jim Stevens, workstation 1, and here's the internal IP address. And we last saw this beacon check in 30 seconds ago. So that is our first beacon listener. All right, let's talk about the HTTPS beacon. Spoiler alert, it is the same as the HTTP beacon, except it uses SSL. The one thing I do want to point out, you can import a valid SSL certificate via your malleable C2 profile. So I very much recommend and ask that you take a look at the malleable C2 documentation on how to do this. One topic I do want to talk about are redirectors. A redirector is a server that sits between your Cobalt Strike instance and your target network. And the redirector forwards traffic back to your Cobalt Strike instance. The value of a redirector is it is a way to obfuscate where your team server really is. It's also a way to give yourself multiple different addresses and address spaces to work with when doing an engagement over the internet. Here are some tips on how to stand up a redirector. You can use IP tables, SOCAT, or another tool to forward traffic to your Cobalt Strike team server as is. Here is a SOCAT recipe to do that. You can also use an Apache or Nginx reverse proxy configuration to act as a redirector for your Cobalt Strike server as well. Finally, you can use a content delivery network like Amazon's CloudFront as a redirector for your Cobalt Strike HTTPS traffic as an option as well. All right, let's go ahead and walk through a basic, air quotes, redirector setup. My goal in this demo is not to make you a infrastructure ninja doing 3 layers of redirectors and domain fronting, but instead to give you a basic mental framework to use when standing up and troubleshooting infrastructure. Because make no mistake, there's no such thing as simple when it comes to infrastructure, and there are definitely multiple points of failure, and troubleshooting and building reliable infrastructure is very much its own skill set. So here we are in Kali Linux, and I'm going to stand up my Cobalt Strike client. We're going to connect to secure.losenolove.com, and here we are. We're going to go to Cobalt Strike listeners, press add. We're going to do EC2 secure HTTP. And we'll configure this to use redirectors later. But for now, I just want to verify I can get a server up. So let's save that. And, well, crap. We have our first problem. Something is taking over port 80 on the server on secure.losenolove.com. That's no good. So let's go ahead and pop open a terminal and let's log into secure.losenolove.com. And let's escalate to root. And let's see what is holding port 80. our very dear, our very close friend, Apache 2. So troubleshooting lesson number 1. Make sure you can stand up a server on your Cobalt Strike instance. Make sure it actually does stand, it does start and there's nothing stopping that. Let's go ahead and stop our Apache server. Verify it's gone. Great. Let's come over to our Cobalt Strike client, press restart, and there we go. The listener is now up and running. I can come over to my terminal, verify that, and we can see that yes, indeed, our team server Java process is holding port 80. Good. This is progress. The next thing I like to do is I like to connect to my team server directly without redirectors, just to verify that I can do that, to verify that I can get a request through. So let's go to View Weblog. And this is where any HTTP traffic will show up in Cobalt Strike. So let's open up a web browser. And let's browse over to secure.losenolove.com. I'll just say /foo. And it looks like that part of our infrastructure is indeed working. That's a big positive, big plus. So it is always valuable to start with the simplest possible case and verify that's working before you introduce any other complexity. So now that we're comfortable that yes, we can talk to secure.losenolove.com, let's stand up our redirectors. So I'm going to get out of that session. And I think we can do this with host names, so I'm not even going to change that. So let me connect over to my first redirector, which is 54.158.156.250. We're going to use my EC2 key, and thank you. We should probably log in as the user Ubuntu and not root. Next, I'm going to just do an apt-get install and bring SOCAT onto this box. And of course, we can't locate the package SOCAT. Why would we? All right, let's do an apt-get update. And let's try to install SOCAT. Money. It worked. And we now have SOCAT installed. Now I'm going to use the SOCAT recipe that I demonstrated in my slides. And we're going to use a program called Screen. Let me just do that a little more slowly to run our SOCAT redirector, but allow us to close, to detach from the shell so that when we log out of the session that we don't kill our program. All right, so I'm going to create a SOCAT redirector. So we're going to do sudo SOCAT TCP4 listen on port 80 and fork each time it gets a new connection. And we're going to do a TCP4 connect to secure.losenolove.com on port 80. And I think that means we are good to go. But as always, let's test. So here's our Cobalt Strike server. And we're going to come over to Firefox. And we're going to do 54.158.156.250. And we'll do a /bar. And yes, indeed, we can see that traffic is getting passed to us. So again, big plus. That redirector is working. And no joke, when I'm standing up redirectors, even simple SOCAT redirectors, I definitely test everything as you are seeing right here, because lots of things can go wrong and it can be a very maddening experience. So let's connect to my other EC2 instance, 34.207.199.101. You can tell I've never been here before. And we're going to do a sudo apt-get update, because I always like to make sure I have the absolute bleeding edge version of SOCAT. And we're going to do an apt-get install for SOCAT. We're going to run screen. And let's do sudo SOCAT TCP4 listen 80 fork. That's what we're listening on. And where we forward the traffic to, secure.losenolove.com, port 80. And that looks good. Control Z to put it in the background and type BG, or excuse me, Control Z to pause, BG to background, screen-D to detach, if I so feel like doing that. And let's test it out. Here's my Cobalt Strike instance. And we're going to do a get on 34, 207, 199, 101. And we'll do /mu this time. And there we go. Our second redirector checks out. I'm very comfortable with this. Now, let's try this out in my lab on my targets that we're using in this particular course. So let's press Control K, and that will clear the weblog. Let's come over here to our listeners, and we can edit. And let's get rid of this host, and let's go ahead and put in our redirectors. So 54, 158, 156, 250, 34, 207, 199, 101. And we'll put in a redirector over here, 34, 207, 199, 101. This looks good. Press save. And there we go. Now let's go ahead and stand up a scripted web delivery that uses our redirector. Attacks, web drive-by, scripted web delivery. And we will put in a redirector over here, 34, 207, 199, 101. Press ... Choose our beacon listener. It's going through a redirector. We'll do 64-bit because we're cool. And we'll just do that on /B as in Bravo. Press launch. All right, press OK. And let's go to our Windows 10 target. All right, here we are on our Windows target. Let's go to Start, Run, paste in our PowerShell one-liner, and jump back to our Kali box. And here we are. We now have a payload calling back to us via our two different redirectors, and it will round robin rotate through those two redirectors we specified in our secure HTTP listener. And secure, again, is the name of the server. And that is basic redirector setup and troubleshooting. I want to give some advice on using a content delivery network as a redirector. First, use a valid SSL certificate. These content delivery networks often require that. Second, make sure that your content delivery network configuration allows both post and get verbs to pass through to your team server. Next, in case you're having trouble, consider configuring your Malleable C2 profile to use HTTP GET to both download tasks and send data back to Cobalt Strike. We will talk about GET-only C2 in the next lecture. I also recommend that you disable all cache options to make sure there is the best likelihood of the redirector allowing the request to pass through to your Cobalt Strike server. Finally, I want to advise you to be aware of transformed requests. Some content delivery networks will take a lot of liberty to move things around in your HTTP request. A common one is CloudFront. CloudFront really likes to rearrange the cookie value. And this isn't a problem, unless your Beacon Malleable C2 profile is using the cookie header to send data back to Cobalt Strike. It's very possible you could break the contract that your Malleable C2 profile creates between the Cobalt Strike Beacon payload and its controller. So just be aware that this is something that can go wrong. I want to talk about a really cool technique that you can use when you have a content delivery network as your redirector. And that technique is called domain fronting. And let me explain a little bit about how domain fronting is even possible, and of course what it is. So a content delivery network is a cache for multiple websites that are the subscribers or customers of the CDN provider. So a client on the internet makes a request to the CDN. The CDN analyzes the request, determines if it has the right response in its cache, and if it doesn't, it reaches out to its customer server to pull that content. And it usually will add that content to its cache. This customer server is called an origin server. And that's something that the customer configures when they create an account with the CDN provider. And there are many different origin servers backed by each CDN provider, because a CDN is a content delivery network for many, many customers. Some of these origin servers are actually content for very highly trusted and reputable organizations or domains. So that's something I want you to keep in mind. But mixed in there, we can become a customer too, and our command and control server can act as an origin server for the content delivery network as well. And so what you end up with, of course, is the state of affairs where many clients are out on the internet making requests to the CDN. The CDN is sending the request to the right origin servers when it needs to. And everything works as you might expect. And of course, our compromised target could itself be calling home to the content delivery network itself, and the CDN can be directing those requests back to our payload controller, back to our Cobalt Strike server. This is why I tell you to configure your CDN redirector to not cache anything, because by default, the CDN wants to cache things to avoid unnecessary communication round trips with its origin servers. But if we're going to use a CDN as a redirector, we want every request to reach us. And that makes sense, right? So without domain fronting right away, to us as an adversary, there's a huge benefit, because the IP space that our target is communicating with is the same IP space of all these other websites and all these very highly trusted businesses. So that right away is an amazing benefit, because a SOC does not have the option to play whack-a-mole blocking CDN IP addresses. They can, but it's not likely to have a good effect on the availability, or excuse me, the ability of their employees and other things in their network to use things on the internet. So that's just using a CDN as a redirector. Now, what is domain fronting? Well, here's the idea behind domain fronting. I, the adversary, want to be able to make a request, an HTTP request, for a highly trustworthy, highly repeatable domain T. But I don't want the request to go to the origin server for that highly trusted repeatable domain. Instead, I want the CDN to direct that request to my command and control server. So in this way, to an outsider potentially, to somebody looking at the traffic here, I look like I'm communicating with this, but in effect, I am communicating with my controller. And this is using highly reputable, trustworthy domains as within your redirectors. It's a really, really cool concept, a really cool idea. And you may ask, is this even possible? And yes, it is. That's domain fronting. That's what I'm going to explain right now. I'm going to show you how that works. So let me get rid of these lines. So let me explain how domain fronting is even possible. So we have a client out on the internet, and it wants to make a request to something that is backed by this CDN. Okay. First, how does the client get to this something X? Well, it does a DNS lookup and on that something X and gets back an IP address associated with the CDN. Okay? And then it just proceeds to actually connect to the CDN, to that IP address. And when the connection arrives to the CDN doesn't know the original host X. It just knows it received a request. It has received a TCP connection, and that TCP connection has to be serviced and parsed to determine which of these origin servers that request is possibly bound for, which cache it should consult, which cache bucket. So how does the CDN pull this information from a request? Well, the common denominator in both HTTP and HTTPS requests is the host header. So you have a host or HTTP request. That's what I'm making right now. And within that request, you have a header, host, and the host happens to contain the intended domain X. Okay? And so what happens is our CDN looks at this value and it uses that value to determine which origin server to pull from if the content it needs to serve is not in its cache. And that's how CDNs work. Now you may be asking, okay, great. Well, how do I domain front? Well, the thing is when you are making an HTTP request as a client, the client doesn't really care what the where you're connecting to. And oftentimes, web clients do have the ability to specify what they want in that host field. And that's certainly the case with Cobalt Strike's beacon payload. Cobalt Strike's beacon payload can change the host header to whatever value it wants. So what you can do is configure your beacon payload so that when it's making a HTTP request, it is instead making a request to a highly reputable and trustworthy domain, T, but instead of having that highly reputable and trustworthy domain T as the host header, which is the default, you can override that. And you can put in, instead, your C2 server. And the CDN will direct the traffic to the right place and use your C2 server's response to respond to this request. So that's domain fronting. That's how it works. And you may say, that's kind of odd. Okay, well, how do I defend against this? Or what are some of the things that can kind of go wrong here? Well, let's say your target network has a proxy server. Okay, I'll put the proxy server right here. And I make a request for a highly repeatable and trustworthy domain over HTTP. So everything is plain to the proxy server. It can see everything. Let's get rid of that. Here's what the proxy server will see. And this is what my client will send. It's going to see a GET on HTTP, our highly trustworthy repeatable domain T, and whatever URI. And it's going to see a host header with our C2 server specified. Now, some proxy servers will actually see that these two things are different, and it will normalize those values and make the host header T. And so what ends up happening here is that your request does go to the CDN, and because that host header is set back to what it's supposed to be, your request goes to the trustworthy and repeatable origin server and not your C2 server. And that's the state of affairs we don't want. So that's plain HTTP traffic. What really surprised me is I thought every proxy would behave this way. And that's not always true. Vincent Yu was playing around with another one, a commercial one, and found that it didn't actually do that normalization. And I was very surprised by that with the HTTP traffic. But that's certainly a very viable and valid defense. Okay, well, what about SSL traffic? Here is what a proxy server sees when we make an SSL connection or an SSL request for a highly trusted and repeatable domain T. The proxy server will see us make a request. It will be connect, highly trusted and repeatable domain T, and then some value for the port, probably 443. And when that's done, what the proxy server will do is it will initiate its own connection to highly trustworthy and repeatable domain T, and it will act as a relay. It will basically make a request, it will connect to that, and it will just forward any traffic it receives from us and any responses it receives from the CDN. And so within this kind of encrypted envelope, we are free to make our request, and we are free to specify our C2 host header, and the content delivery network will indeed route our request to the right place. And everything works the way we like. And this is why SSL is so desirable when you're doing domain fronting. Because ideally, the proxy server does not have visibility, that's my attempt to draw an eye, into what is happening within the actual HTTP request. Now you may say, aha, not so true, Raphael, because in our company, we actually man in the middle all SSL traffic. So our proxy will actually look at everything that's going through, and we have a chance to actually correct those host headers from your C2 to that highly trusted and repeatable domain, or even to use that as an indicator of compromise. And maybe that is true in your customer environment. Maybe. I mean, that's part of red teaming, right? We're actually kind of testing and exercising these assumptions, right? Exercising these ideas. But here's the thing. Not every organization will man in the middle every single domain. Because maybe the domain you find that's highly trustworthy and reputable is something in finance or healthcare. And one of the things that might be a blind spot for that SOC is they do not want to man in the middle traffic of employees looking at their bank account or even maybe looking at information from their healthcare provider. And that becomes a blind spot. And I'm not arguing that that's a bad blind spot to have. I certainly agree that, hey, it's good not to want to accidentally see that stuff. But what I'm pointing out is the adversary don't care. They're going to take advantage of these things. So that's a blind spot where even in organizations that might be doing man in the middle of SSL traffic, that they might actually give a free pass to certain types of domains. And so that's something to be aware of and that you could possibly use to be successful even in that situation. There's still another wrinkle. You may have heard some people espouse that, hey, domain fronting is dead. And they're going to say, hey, I heard that provider X made it so that domain fronting doesn't work anymore. And you may be wondering, what's that all about? Well, let me explain another mitigation against domain fronting, something that is within the control of the CDN provider itself. The host header is great because the host header is a chance to figure out where to send traffic over HTTP and HTTPS. But there's one other indicator that can help. So here's our HTTP request, right? And here's our host header that says where we want things to go. And if we're using SSL, or really, I should say TLS, there is a field in this layer called SNI, or Server Name Indication. This field has the host the request is bound for. The server name indication field is something that a CDN can look at to determine where should the request go, or it's something else that the CDN can look at to try to normalize. So some CDNs do actually look at this value, and if it gets a request for a highly trustworthy and repeatable domain T, it might actually normalize, and it sees a host header of C2, it might actually notice the difference and take some sort of action, such as normalizing the host header. Okay? So when people say that, hey, provider X does not allow domain fronting, this is the kind of thing that they're referring to. And all of that explanation was the lead up to this one slide talking about one field. If you want to do domain fronting with Cobalt Strike, you no longer have to customize your profile for it. You can set the HTTP host header for the stager, how Beacon downloads tasks, and how it sends data back by configuring the HTTP host header value in the listener configuration dialog. So if you want a domain front, this is how you do it through Cobalt Strike. In Cobalt Strike 3 and earlier, the model for distributed operations was to have one server per egress infrastructure. So if you wanted to have a server for post-exploitation with a normal HTTP beacon and a variation that could do get only C2, you would need two servers. In Cobalt Strike 4, you can now consolidate variations of the same infrastructure to one server. And briefly, here are the things that support that. First, you can define multiple egress listeners. That is now okay. Second, you can do port bending. So if you want two HTTP beacon listeners to share port 80, bind them to different ports and set up redirectors that listen on port 80 but actually direct traffic to your Cobalt Strike server on the correct port. Third, if you want to have variations in your indicators, Cobalt Strike's Malleable C2 now supports the concept of profile variants. And a profile variant is a way of defining multiple variations of the same profile in one file. So each of your listeners can have a different profile variant, and therefore they can have different traffic, different indicators. Finally, for post-exploitation and pivoting, all of these listeners that are calling back to the same server can benefit from peer-to-peer pivoting with the same set of TCP and SMB beacon listeners. So that's server consolidation in Cobalt Strike 4. I want to briefly show you what I imagine as this server consolidation model in practice and what it looks like. Here we have our team server, okay? And we've got over here our compromised host. And let's say we want the compromised host to beacon back to listener 1 on port 80. And that listener 1 happens to use a default set of indicators for our profile. So whatever is just the default. Well, I can have a redirector out here, redirector 1, that also listens on port 80 and directs traffic to this listener. Make sense? Right. So my compromised system can beacon back to this. Now let's say I consider it advantageous to have a second listener that happens to use a variation of the current profile that can do a get-only C2. Maybe that's what it's called. It's called the get-only C2 profile variant. And I also want listener 2 to be reachable on port 80. Previously, you would just be required to stand up another team server to have this option, but you don't need to do that anymore. Now you can create a redirector, maybe redirector 2, that listens on port 80, and it calls back to listener 2, which is indeed configured to do C2 to port 80, but is actually bound to, say, port 81. And this way, our redirector can call back to listener 2 on port 81 and pass through traffic it receives. But for the perspective of a compromised target, it's just beaconing back to your redirector 2 on port 80. So here you have two listeners, one team server, different indicators, but using the same port effectively. So that's what it looks like to do server consolidation. Another major benefit of consolidating operations where you can to a single server is if you have a complex pivoting situation where you've got multiple levels deep of compromised targets that are being controlled with either the, let's say the SMB beacon, or even we'll say the TCP beacon. You can control this mesh with any of your accesses that are calling back to listener 1 or listener 2. So that's another handy benefit of consolidating infrastructure to a single team server where you can. Let's talk about the DNS beacon. The DNS beacon is a payload that uses DNS lookups to communicate with a Cobalt Strike team server out on the internet. And I want to show you what this communication process looks like. A common message that the DNS beacon sends is its identifier prepended to a host that is a domain or subdomain that your Cobalt Strike team server is authoritative for. Okay? And when our DNS beacon tries to make this kind of a lookup, the thing it's most likely to do, or I should say really this is up to the compromised system, so the thing the compromised system is most likely to do is what is called a recursive query. And a recursive query is where the local system says, I don't know what this host is, it's not in my cache, let me consult another server that I'm configured to ask. So it contacts its local DNS server and says, local DNS server, do you know the response or value of 1234.profiles.losenolove.com? And that local DNS server is going to look in its cache, and it's going to hopefully find that no, I don't. But it doesn't respond to our compromised system yet. Instead, it sets to work. And most likely, that local DNS server is going to do what is called an iterative query, where it works to find out the value of this host. So the first thing it does is it reaches out to a system called a root server that is baked into its software or its configuration. And the root server is a top-level server that is kind of authoritative for the internet. So it contacts the root server and says, root server, do you know the 4-byte response for this A record lookup for 1234.profiles.losenolove.com? And that server is, of course, going to say no. It doesn't actually know that answer. And what it's going to reply with is advice that our local DNS server instead ask the server that is authoritative for the .com domain. So it's going to give us back that response. And our local DNS server, undeterred, is going to try again. So what it does is it reaches out to the .com server. It says, .com, do you know the 4-byte value, the A record value of this request? And the .com server is going to say, no, I don't. And it's going to direct us to instead consult the server that is authoritative for losenolove.com. So it's going to send that information back to us. The local DNS server will then reach out to that server, which in real life happens to be one of GoDaddy's name servers, and it will ask GoDaddy, do you know the 4-byte A record value for 1234.profiles.losenolove.com? And GoDaddy is going to look at its zone files and it's going to say, no, I don't. But I do know a server that is authoritative for profiles.losenolove.com. Why don't you ask it? And that's the answer our local DNS server gets. So our local DNS server then makes another query, undeterred. It reaches out to, hey, look, it's our Cobalt Strike team server. And it asks our Cobalt Strike team server, do you know the 4-byte value, the A record response for 1234.profiles.losenolove.com? And our Cobalt Strike team server parses the query, pulls out this identifier, and checks if there's any tasks. And if there are, of course, it very much responds back and says, yes, I do. Here's the response. And the local DNS server, satisfied in its work, conveys that response back to our compromised system. And our DNS beacon is able to consume that information and act on it. So this is how the DNS beacon communicates. And it uses this type of process to beacon back to us to check if there are tasks, to download tasks, and to send data back. And when it sends data back, what it's actually doing is putting all that data into a very long subdomain of its authoritative domain. So that's the DNS beacon. I hope you enjoyed that lovely rendition of The Little DNS Beacon That Could, read by Raphael Mudge. This slide doesn't have much new information. To configure the DNS beacon, you want to put in the host that it will call home to. These are going to be domains or subdomains that your Cobalt Strike team server is authoritative for within the DNS system. If you are going to stage over DNS, you do want to put in a DNS stager host, and that again needs to be a domain or subdomain that your Cobalt Strike team server is authoritative for within the DNS system. A C2 port of port 53 is implied because we're not actually just communicating using DNS-like queries to something directly. We are relying on the target's configuration, so we don't get a big say in a port. But if you want to bind the Cobalt Strike DNS server to a different port, in case you want to do a redirector, you can, so that's what the bind value is for. I want to share with you a very sad red teaming story. I'll draw a little tear right there. Years ago, I had a beacon payload running on a compromised target, and I had my team server over here. And back then, the way the DNS beacon payload worked, and by back then I'm talking about 2013, the way the DNS beacon payload worked is it would periodically make an A-record request to that domain Cobalt Strike is authoritative for. And in making that A-record request, it's asking Cobalt Strike, do you have something for me to do? And if the answer is no, Cobalt Strike would send back a response of 0, 0, 0, 0, which meant I have nothing for you to do. But if Cobalt Strike sent back something else, not 0, 0, 0, maybe it's IP address, this was a cue to Cobalt Strike, or excuse me, to the Cobalt Strike beacon payload to make an HTTP request to go figure that IP address to download its taskings. Okay? And this is how the DNS beacon used to work. And the purpose in doing this was to minimize how often the compromised target communicated with us over HTTP. The DNS beaconing was exactly that. It was just a way of saying, I'm here, but I'm not going to actually communicate with you directly so that, it's harder to tell that this system is compromised. So it's a pretty cool OPSEC measure, especially when you realize it's from 2012, because that was something introduced with the original beacon payload. So anyways, one day I've got this compromised target, right? And I do have a tasking for it. So the beacon tries to connect back to me over HTTP. So it makes an HTTP request, and very sad red teamer me, I find that the request was squashed by the local firewall for that network. And I ran into a situation that I called the child in the well, because the DNS beacon could reach me by making an A-record request, but the HTTP request couldn't reach me. So I knew the agent was there, I knew it was running, but it was crying out from that compromised network, and me, the loving payload mother, I can't do anything to save it. I can't do anything to love it. It's just there, and it's out of my control. And trust me, there's nothing that hurts a red teamer more than having a payload that you know is there and you know needs you, but you can't reach it. You can't communicate with it. And so, yeah, I lost that network and I lost those payloads. But I resolved this wasn't going to happen again. And so I introduced a command into Beacon, the mode command. And the mode command, the way it works is it's mode channel. And the mode command was a way of signaling how I wanted the DNS beacon payload to download tasks. And yes, there was a HTTP mode. And the HTTP mode was the default. So that's right here. But similarly, if I didn't want it to use HTTP because of the child in the well situation, I could very easily send back something else like 000-255 hypothetically, which means use A records because I know those can get through to download your tasking. And so the mode command became a way of recovering the agent so it could download all of its taskings, one 4-byte A record request at a time, to figure out what it was supposed to do. And so the mode command became a way to recover the agent. And that's where this particular capability in Cobalt Strike came from. The mode command is still in Cobalt Strike 4. Things are a little different. The DNS beacon is no longer a mix of an HTTP and DNS beacon. The DNS beacon does not have an HTTP channel anymore. Its default mode is DNS text to download taskings over DNS text records. But if you want to change the data channel, you still can do that. There's mode DNS to have the DNS beacon download tasks one A record request at a time. You can use DNS6 to have the DNS beacon download tasks using a quad A record. And again, the DNS text channel is a way of doing DNS text records to download taskings. One thing that's interesting, which I will speak to in the next lecture, is that the host name, the length of the host name to send data back, is also affected by each of these modes. The DNS text record channel, the DNS text, will use the maximum amount of hostname space that your profile allows. But DNS and DNS6 will actually cut that value down. And the reason they do this is because in some networks, very long host names are automatically denied and just cut off. So the mode command, even today, even as a pure DNS beacon, is still a way to recover the agent if your initial C2 scheme isn't working for you. Let's talk about the DNS beacon setup. Our goal is to make our Cobalt Strike team server an authoritative name server for one or more domains or subdomains. To do that, first, have the ability to edit the zone file for a domain that you control. And that could be editing the zone file on a Unix server, or it could be a web interface that lets you change records for a domain that is being managed at the top level by some provider that you paid. Next, create an A record for your Cobalt Strike system. An A record is just a way of saying, hey, this host resolves to this IP address, this IPv4 address. So for example, create an A record to point malwarec2.losenolove.com to say 184.73.25.227. That's what this is showing right here. So once you've got an A record, you now have a way of, by name, referencing your Cobalt Strike team server system. Next, create an NS record that points to a subdomain or domain to the fully qualified domain name of your Cobalt Strike system. So here, I have NS records within the losenolove.com domain. And I am delegating free picks, game, and profiles to malwarec2.losenolove.com. That's what these records look like. At this point, the Cobalt Strike team server, malwarec2.losenolove.com, is now the authoritative name server for freepicks.losenolove.com, game.losenolove.com, and profiles.losenolove.com. Anything dot those subdomains is automatically going to come to our server, and it's going to get a chance to respond to them. Let's take a quick look at the setup and use of the DNS beacon. So I'm going to start a Cobalt Strike client, and I'm going to connect it to malwarec2.losenolove.com. And here we are. I also have a terminal open to where I am running the malwarec2.losenolove.com team server from. Let's go ahead and create a DNS beacon listener. Go to Cobalt Strike Listeners, press Add, and choose Beacon DNS as the payload. We're going to call this EC2 DNS. Now for the DNS host, we need to put in one or more domains that our Cobalt Strike team server is the authoritative name server for. And again, that means we've created an NS record that delegates this domain or subdomain to our Cobalt Strike team server. So let's go ahead and put in freepix.losenolove.com. And I'm comfortable with that. Press save. And there we go. We now have a DNS beacon listener running on this Cobalt Strike team server. And if we come over here to the terminal, you can see that yes, indeed, the DNS server has started, or our DNS listener has started. Let's test it out a little bit. The thing I like to do is to issue a message like test.freepix.losenolove.com. And if everything works, we should get back the DNS idle response for the team server. By default, this is 0000. Let's try something let's make a typo here. If we type something that doesn't exist, of course, we don't get back an answer. So I just want you to see that difference. If you do a test lookup and you don't get back that idle response, something is wrong and you'll want to troubleshoot what's happening. Another thing you can do that's kind of cool, just to see what I showed you in the DNS beacon that could slide, is you can do a trace of an iterative query. So if we do dig plus trace test.freepix.losenolove.com, you can see the path made to actually resolve this domain to something. And dig starts out by reaching out to the root servers for the internet. And it keeps getting referred down until we get to, let's see here, the root server for the internet, the root servers for .com. And then we get the authoritative name server for losenolove.com. And finally, we end up at the authoritative name server for freepix.losenolove.com, malwarec2. And we get a response to our query from malwarec2.losenolove.com. So that's a way of seeing what I showed you a little bit earlier. But I think we're good to go. This DNS infrastructure seems to be working. And again, most of the time when I'm testing, I just do an NS lookup, but on the correct domain. And that's how I make sure everything is sane and working. All right, let's go ahead and create a PowerShell one-liner to run our DNS beacon. So we're going to go to attacks, web drive-by, scripted web delivery. Press ... Choose our EC2 DNS beacon. We'll do a 64-bit payload and press launch. And there we go. Here's our one-liner that we can use to run the DNS beacon on a target. Here we are on a Windows 10 target system. And again, we're just going to paste in that one-liner, press OK, and jump back to our Kali Linux box. And here we are back in Kali Linux. And you can see we have what some people like to call a ghost beacon. Really, it's not a ghost. It's just a beacon that we don't have any metadata for yet. And by the way, anything that makes a lookup on our team server that matches a pattern that looks like a DNS beaconing message is going to create a ghost beacon. So be aware of that. But to get the beacon to send metadata to us, what we need to do is right-click, interact, and give it something to do, some reason to talk to us. So I'm just going to use the sleep command and tell beacon to check in every 5 seconds instead of the default 1 minute, which is in the default profile. And when the 1 minute time rolls around, you will see we now have metadata for this particular beacon. We can see it's PowerShell XE in PID 7780. It's a 64-bit beacon, and now it's checking in every 5 seconds. So that's the DNS beacon. And the DNS text record channel is pretty performant. You can do a lot of things with it. For example, if we take a screenshot, the DNS beacon is going to download the screenshot tool over the course of multiple TXT record requests by default. And once it gets the tool and runs it, it will send a screenshot back to us via several long host names. And I'm showing you this because this is a very normal routine thing you might do with a beacon. But I want you to be aware that DNS is a constrained channel. It takes a lot of requests to download a capability and to get output back, especially when it's something as big as a screenshot. But if you're patient, the capability does work. It's pretty robust, and we will actually get the result we expect back. And I do want to point out that as I'm doing this demo, everything is over the internet. So this is a realistic demonstration, realistic latency. And there we are. We now have our screenshot. And go to View, Screenshots, and we can see that this is the screenshot of our Windows 10 target where we ran the DNS beacon. So that's the TXT record channel, and the TXT record channel is the best you're going to get with DNS. There's another channel, DNS6, where Cobalt Strike will use, again, Quad A records to download taskings and shorter host names to send data back. You could probably take a screenshot over a Quad A channel. It's just going to take a lot longer to download the capability and to get the data back. And if you're using the A record channel, for low bandwidth things, it's just fine to control the beacon. But if you try to take a screenshot or do something that is very large, when you chunk it up into 4-byte chunks, just be aware it's going to take a really, really, really long time. I have actually escalated privileges and controlled a namepipe beacon over an A record channel before. I think in that one network it took a couple of hours to actually stage everything, but it can be done. But just be aware that if you try to do something really big, like run Mimikatz over an A record DNS channel, it is going to take a very, very long time for your beacon to actually download that capability and run it. And also be aware that if you use something like the A record channel, that you are going to be spamming the wire with a lot of DNS requests when you try to do something. The benefit of the A record channel is that if you can beacon, meaning you can actually see the agent checking in over DNS, the A record channel is going to likely be able to actually communicate with you. And I very much see this channel as a way to recover the agent when using DNS text records as a channel isn't working for you. So that's a little bit on the DNS beacon. Let's talk about the SMB beacon, or if I knew what I was doing in 2013, I would have named it the named pipe beacon. The SMB beacon is a payload that uses named pipes, which is a mechanism for inter-process communication in Windows to communicate peer-to-peer. And in this diagram, you can kind of see what I mean by that. Here we have our Cobalt Strike controller, and we have a compromised system that is beaconing back to it, and that compromised egress beacon is also linked to a child beacon. And so anything that we ask this beacon here to do is relayed back to its parent, and of course back to our team server. And that's the idea of peer-to-peer communication in Cobalt Strike. One thing that this particular diagram doesn't do justice to is the idea that you can have your team server, and yes, you can have your initial foothold beacon, and that initial foothold beacon is of course beaconing out. And that initial foothold beacon can of course control multiple child sessions over named pipes. So there's an SMB beacon connection, there's an SMB beacon connection, and there's an SMB beacon connection. But your SMB beacons can control other SMB beacons as well, either on the same host or even on a remote host, which is something we'll talk about in a moment. I mentioned that the SMB beacon can control child beacons on a remote host. That is true. When you use a Windows named pipe to communicate between two processes, one is on one host, the other is on another host, Windows will encapsulate that communication in the SMB protocol. This is why I call the SMB beacon, because it is a way of using traffic encapsulated within normal port 445 SMB traffic to control a beacon on a remote target. To use the SMB beacon, you will need to create a listener that defines the properties of the payload. So give it a name and choose your payload type as beacon SMB. The only option you can really set right now is the pipe name, although I'm sure many of you are happy you finally have that ability to do that outside of a profile. And yes, you can define multiple SMB beacon payloads on a single team server. That's no problem. One thing that is really cool about the SMB beacon is that you can disconnect from it and reconnect to it from another beacon at a later time. And in this way, the SMB beacon becomes a backdoor to maintain control of a target, even if you don't want to actively communicate with it all the time. To link to an SMB beacon, use the command link inside of the beacon console. So do link, hostname, and the pipe name. You can tab complete the pipe names, so you don't have to remember them character for character. And when you tab complete pipe names, Cobalt Strike will actually pull that from your listeners. So that's really, really handy. If you want to disconnect from an SMB beacon, use unlink, the host name, and the process ID, and that will have your current beacon disconnect from its child beacon, and that beacon will go into a state where it is now waiting for a new connection from another beacon parent. When you link to a beacon peer, there are a few things that can go wrong, and you may get back a message with a number saying, hey, I couldn't link to that beacon. Those numbers are error messages returned by Windows, so you can look those up if you want to, but here are a few common ones. Error code 2 is file not found. If you get an error code 2, that means there is no beacon for you to link to. If you get error code 5, that means you do not have permission to link to that beacon. You do not have permission to access that named pipe. If it's on a remote target, it might mean that your current context does not have valid credentials in your current what's called access token to authenticate to that system and connect to that pipe. Or it might mean that your current context simply doesn't have permission to access this pipe, which could be locked down for some reason by the system. If you get back error 53, bad net path, it just means you have no trust relationship at all with the target system. And that doesn't mean there's a beacon there. It doesn't mean there's not a beacon there. It just means the remote system isn't talking to you. It's like it wants nothing to do with you. It doesn't know who you are. So those are a few common errors that you might see. Here we are in Kali Linux, and let's take a look at the SMB beacon. Here we have our foothold from the previous demo calling back over DNS. Let's go to Cobalt Strike Listeners, press Add, and let's go to Beacon SMB for the payload. We will call this something easy, maybe EC2 SMB. And this is the default pipe name. We'll leave it, press Save, and there we go. We now have a Windows Beacon Bind Pipe Listener or payload configuration. And let's use it to do something. Let's right-click on this initial access. Let's go to Access Elevate, and we will use an exploit that we'll talk about much later called UAC token duplication, and that is a way to bypass UAC. And let's select our SMB beacon listener, press choose, hit launch, and if all goes well, we will get an elevated session. One thing to point out is that we are actually pushing our payload over DNS. So it is going to take a minute because the DNS beacon has to download the SMB beacon and the attack and run it. So that's what we're waiting for right now. Sometimes things are faster with an HTTP foothold, but I've always found it cool that you could operate over DNS, so that's why I like to demo this. And there we go. We now have our elevated session as Jim Stevens. You can tell it's elevated because of that star and the red monitor. So that is an example of chaining two beacons. This is the parent, this is the child. And you can see the little link. Let me interact with this beacon. If we want to, we can go to Access Elevate, and we can elevate again, this time using Service EXE, which is like something called PsExec. It creates a service locally and runs our beacon. And this is a way of getting into a system context. And so we're just letting this download and run over DNS again. And this is an example of using the SMB beacon for pivoting context to context on one target. And that's something you'll do a lot with the Cobalt Strike product. And there we go. We now have our system beacon. And you may be looking at this saying, okay, that's cool. There's 3 beacons. I know they're somehow chained, but how do I keep track of this chaining? Well, let me show you. Go to Cobalt Strike Visualization Pivot Graph. The pivot graph shows the parent-child process relationships of your egress and your child beacons. So I'll just bring one more item in here just to show you. I'm kind of getting a little bit ahead of things, but we're going to just do lateral movement real quick. to jump over to another target. So I'm verifying that I have administrator rights as the current user on a system called file server. And I'm going to use a lateral movement option called PSExec. And we're going to do, actually we'll do PSExec 64 for 64-bit PSExec. And we'll jump over to the file server and we'll use the name pipe beacon. And again, this is all over DNS. And if all goes well, another 45 seconds or so, we will have another link in our chain on the file server system. And I'm doing this again to demonstrate that the peer-to-peer pivoting is not just on one system, but it is also potentially from one system to another when you're doing lateral movement. And there we go. So now our pivot graph shows that we have control of the file server system. Pretty cool, right? What about linking and unlinking? Let me demonstrate that real quick. Let's come over here and let's do unlink. And we're going to unlink from ourselves. And we're going to unlink PID 1052, which is this beacon right here. And of course, if we tab complete through that, we would get all of our different options. But let's unlink Jim Stevens Workstation 1 at 1052. And you can see that those SMB beacon links are disconnected. Now, if we come over here to the file server, and if we want to, we can link to Workstation 1, MS Agent, 4EF8, and there we go. We've resumed control of this beacon session via another beacon session. And when you resume control and you're multiple levels deep, just give it a few moments and the other children will check in as well. So that's an example of using link and unlink with the SMB beacon as well. Cobalt Strike does have a TCP beacon. Conceptually, it is very similar to the SMB beacon. It is a beacon that can be controlled by a parent beacon, which can be a TCP beacon, an SMB beacon, or one of your egress beacons. When you stand up a TCP listener, or really you're configuring the payload, you get to choose the bind port, and you get to choose whether or not the payload should always bind to localhost only. The localhost only option is really useful if you're planning to use the TCP beacon for localhost pivoting, so for privilege escalation or moving to another context on the system. To assume control of the TCP beacon, use the connect command with a host and a port, and you can tab complete the ports, very similar to the SMB beacon. And to disconnect from a TCP beacon, use the unlink command. One other thing to point out is that the TCP beacon is, again, very similar to the SMB beacon. When you disconnect from it, the TCP beacon then goes into a state where another beacon can connect to it later, or I should say another session. Let's take a quick look at the TCP beacon. Again, Cobalt Strike listeners, press add, and we will create a EC2 TCP beacon, beacon TCP. And this one I will bind to localhost only. Press save, and there we go. We now have our TCP beacon. One thing I like to do, or I anticipate I will like to do, it's a new feature, but one thing is for listeners that you expect have a specific purpose, consider giving them a color that indicates that it might be a different beacon from the others. For example, I'm going to flag this one as yellow, which is my way of indicating in the tool or to other operators that, hey, this is a localhost only beacon, just so that the operator doesn't miss that and try to use it for lateral movement. Okay, let's take a look at using the TCP beacon for something local. And I know what we'll do. That'll be kind of fun. Let's use the TCP beacon to create a session as another user. So what we're going to do is right-click Access, Spawn As, and we're just going to create a beacon running as the user. What a hog. Why not? And she is a domain user on the domain corp. We're going to hit ... and we will choose our TCP beacon. Hit choose, hit launch, and if all goes well, we will end up with a session as the user What a Hog linked through Jim Stevens. And again, remember that our egress is DNS here, so we're actually pushing the entire payload over DNS. And that's not necessary for this demo, but it's my way of making the demo take a lot more time. In fact, I do want to point something out that is very, very relevant. If we click on the toolbar, there are shortcuts here for different menus. This one right here is to go back to the sessions table. And I want to point out a column, and that's the listener column. The purpose of the listener column is to quickly let an operator know which beacon or which type of channel your chain of things is egressing through. Because if you have an HTTP beacon here and a DNS one, you really want to know which one is the parent of your beacons so you know the performance characteristics of that channel. So that's the listener column. And we can see that we did indeed get our What a Hog beacon. And if we click over here, we can see the pivot graph. And there's What a Hog. Another thing to point out, orange lines are the SMB beacon and teal lines are the TCP beacon. So that's what that looks like. So that's a little bit on the TCP beacon. I suppose real quick, I can show you linking and unlinking to it just to convince you that what I explained in the slides is real and works. So there we go. We've disconnected from it. And if we come over here, let's go ahead and connect to 127.0.0.1, port 4444, and there we go. We've resumed control of this TCP beacon from another access. So that's what I wanted to show you with the TCP beacon. External C2 is a specification that allows a third-party program or third-party toolchain to control a namepipe beacon, read data from it, and relay it back to the Cobalt Strike product. Likewise, taskings destined for that beacon can be read from Cobalt Strike and relayed back to the namepipe beacon over a namepipe. This idea that a third-party program has an easy way to get in the middle of Cobalt Strike's communication and relay things back and forth is the idea behind external C2. To use external C2, if you have one available that you would like to try, you will need to create an external C2 listener in Cobalt Strike. An external C2 listener is not a normal payload listener. You can't pass sessions to it or anything like that. But you can create an external C2 listener to stand up the external C2 server in the Cobalt Strike product. The external C2 server is what these third-party client-server systems connect to interface with the Cobalt Strike product for communication purposes. You can bind the external C2 server to a specified port, and you can choose to have it bind to localhost or not. The decision to bind to localhost is going to be very specific to how you're using Cobalt Strike. This is not a privileged RPC or anything like that. The only thing external C2 can do is receive data from a beacon and relay encrypted tasks back to it. It's no different than the HTTP or DNS beacon servers in terms of capability. It just happens to have less wrapping. Here we are in Kali Linux. Let's take a look at external C2. I'm going to create a listener, Cobalt Strike Listeners. Press Add, and we will call this external C2 TCP. And we will select external C2 as our payload type. Port 2222 is OK with me. We now have an external C2 server running on our malwarec2.losenolove.com team server. Now, what are we going to use as an external C2? Well, let's go to the Cobalt Strike website, click Support, and go down to External C2. This is the documentation on External C2. I do link to a few third-party projects you can look at if you want to get an idea of the different frameworks or even ready-to-use tools available to play around with External C2. But for this demo, we're going to use the example inside of the Cobalt Strike external C2 specification. And that example is a simple C program that runs on the target, connects to the external C2 server directly, requests a payload, and relays frames back and forth. That's it. So the program is actually here in the external C2 specification. And I actually built it already. I had to copy and paste this program out of the PDF file. And I built it with the new compiler toolchain Windows cross compilation toolkit. So the minimal new for Windows 32. If you just run build.sh here, that'll build it. That's what it looks like. Okay. Now let's go ahead and run the external C2 combination client and server, this external program. So here we have Cobalt Strike. Our external C2 server is on port 2222. Here I am on my Windows 10 target, and I have my previously compiled external C2 over here. And we're just going to run that. And our example does tell us what its arguments are, which is host and port. And I want to say the example requires us to use an IP directly. So I'm going to just look up malwarec2.losenolove.com and do 54.80.166.26, port 2222. Whoops. Not 266.26. And there we go. Our external C2 client is now running and connecting, in this case, directly to the external C2 server. Here we are back in Kali Linux, and you can see that I have a session associated with my external C2 TCP listener, and it's user Jim Stevens running inside of example.exe, which is a 32-bit program, PID 4656. So that's an example of using an external C2. And there we have it. In this lecture, we covered listener management. I showed you how to stand up listeners that manage payload configurations and their controllers. And I walked you through the different types of beacon payloads. We talked about the HTTP and HTTPS beacon payloads and redirectors. We talked about the DNS beacon. I also walked you through the SMB and TCP beacons as well. We concluded with a discussion of external C2. This concludes infrastructure, which is part 2 of Red Team operations with Cobalt Strike.